Okay, I think, excuse me. Okay, I think that's about everybody. So today will be a small class. Okay, so we can keep it a bit more informal. Yeah. Okay, so first announcements. Okay, so online quiz 2 and your written quiz 2 is coming. It's one thing after another. Okay, so online quiz 2 is coming out in 2 weeks' time. So week 11 during lab. Okay, same as your online quiz 2-1. Okay, written quiz 2 will be coming up in 3 weeks. Okay, in week 12, and it will be during the lecture. Okay, so I will take half of the lecture time, about 40-50 minutes to go through the lecture. Then about 40 to 45 minutes, you will do your quiz 2. Okay, so quiz 2 will be a short one. It's only 6%. Okay, so it's a slightly more weightage than an online quiz. Okay, but it's basically to prepare you for the exam. Okay. So for both, the material you'll be tested on will be from lecture 6 to lecture 9. Okay, lecture 6 to lecture 9. So it'll be from MST, no, BFS, DFS, all the way until this one. Okay, yeah. Okay, so outline for today's lecture, we'll be continuing the discussion on single source shortest path problem. Okay, so we'll discuss 4 special cases, okay, of this very classical SSSP problem. So in the previous lecture, we already saw one very general way of solving this, okay, which is using Bellman-Ford, okay, which you can apply to any general weighted graph. Okay, it can be even used to detect whether there are negative cycles, okay, in your graph. Okay, but if there are special cases, okay, for your inputs, okay, your special input, then there are different, actually more efficient or different algorithms that you can use okay, to solve your SSSP problem. Okay, so here we will look at 4 different cases. Okay. Okay, so basic forms and variants of a problem. Okay, like I said, we will be revisiting the SSSP problem. Okay, so the idea from the previous lecture, okay, also this lecture and your PSs so far. Okay, so a certain problem can be made simpler if you make some assumptions about the input. Yeah, for example, if I say that the input is just a tree, then your PS usually subtask A. You find, oh, very easy, I can use a simpler algorithm to solve it, okay, very quickly. Okay, so these variants or special cases have better algorithms, okay, than the very general algorithm to solve it. Okay, of course, in certain cases, variants actually make the problem more complex rather than simpler, but usually, in most cases, it makes it simpler. Okay, so let's look at 4 different special case, okay, for our SSSP problem. The first special case is when the input given to you is a weighted graph, and it's a tree. Okay, the weighted graph is a tree. Okay, so for example, something like this. Okay, this is a tree. Okay, it might not look like a tree, but it's a tree. Right? Okay, it's a tree. Okay, so when the weighted graph is a tree, then solving SSSP problem becomes much easier, right? Because every path in the tree is also the shortest path. Why? Why? Yes, in the tree there's only one path between any pair of vertices. It's the smallest connected graph. Okay, so there are no extra edges to form any cycles. Yeah. So there are no negative weight cycles, right? Why? Because there are no cycles, correct? Yeah. So no cycles, no negative weight cycles. Okay? So how do you solve this? You can just use any of your big O of V graph traversal algorithms, like BFS, DFS, okay, you can solve it. Okay. Now question 3, why is it big O of V and not big O of V plus E for this case? BFS is big O of V plus E, right? Yeah, exactly, because in this case for a tree, number of edges is basically V minus 1. So it's big O of V, okay? So important, you can try this on PS5 subtask A. So PS5 has been released already this noon. Yes, it has been released, so I don't know whether you all checked it on CodeCrush. It has been released, okay? So you can try it out, okay? Use this idea for subtask A. Okay, so let's try this, okay? DFS on the tree. Okay, let's look at our visual algo. Okay, so here I give you a tree, Okay, basically, you can see there's a tree. There are no cycles in this tree. Okay, you can imagine that these edges, right, they're actually undirected edges, or in this case, they are bidirectional edges lah. Okay, so these bidirectional edges here have the same weight in both directions. So, I mean, you can consider these edges as basically trivial cycles. Okay, so it's not totally true that there are no cycles in the tree, but these are very trivial cycles. We don't care about trivial cycles. Okay, it's easy to discard these kind of trivial cycles. Okay, so let's try DFS. Okay, on this one, you have to compute the shortest path from source vertex 0 to every other vertex. Okay, let's try. So, if I just do DFS, I start from vertex 0, right? So, same thing with your Bellman-Ford, okay, or the other variant, okay, using DFS. What you do is that at the beginning, you set source to have shortest path estimate 0, right? Because that's the only one you know for sure, yeah. And then the rest will be infinity. Okay, so you need your D array, and you also have your predecessor array. Okay, when you start from 0, what do you do DFS? You will recursively visit which one? So we will visit all the neighbors of 0, right? So in this case, we will visit them in increasing vertex number. Okay, so we'll go to 1, right? Go to 1, I will just relax this edge. So this will be what? 0 plus 2, it becomes 2. Yeah. So from 1, I will try to visit its neighbors, correct? Since it's a bidirectional edge, of course, it will try to go to source. Okay, but it's very easy to detect, right? These kind of cases. I just see whether it is infinity or not. If it's not infinity, I don't have to do anything because that is something I've already processed. Okay, so it won't do anything to source, and it will try to recursively go to vertex 3, right? And then relax the edge. Okay, from 2 to 3, from 1 to 3. Okay, so it's 2 plus 9 gives you 11. Okay, and from vertex 3, it will try to go to 1. Well, that's its predecessor, so it won't do anything. And then after that, it will recursively go to 2. Right? Again, relax this edge, 3 to 2. So you get 16. And then at 2, you will try 3. 3, nope, it's already fixed. You already computed the shortest path cost. Then 2 is finished, right? So I will come back to 3. 3 will now try 4. Right? So 11 plus 1, yeah, update. Okay? And 4 will try 3. Nope, nothing because 3 already done. And come back to 3. 3 finish. Go back to 1. 1 finish, all neighbors go back to 0. 0 will try 5. Then you update the shortest path cost. Okay? And 5 will try 0, cannot do anything, and then go back to 0, finish. So using DFS, basically I have found the shortest, I've computed the shortest path cost to every other vertex. Okay? And basically, since this is the tree, the shortest, single source shortest path spanning tree is also the tree itself. Yeah? Okay? Okay, if we add negative weight edges, do you think it will change anything? It won't change anything because it is still just one single path, right? There are no negative cycles, so there's no problem. Okay. Okay, second special case is when the graph is unweighted or the same constant weight. Okay, so this one we already discussed last week, right? So the way to do it is use DFS. Okay, the O of V plus E times DFS. Okay, so this one I will not go through it again. Okay, so basically I think you should be quite familiar with this now. Okay, so important note, on unweighted graphs, okay, use BFS. On a tree, you can use either BFS or DFS because there's just one single path, no problem. Okay. Okay, so I'll just skip this. You can try this on your own. Okay. Okay, next case. This one is a very interesting case. Okay, this is a case where the graph given to you, the input given to you, is a weighted graph that is directed and acyclic. Okay, it's a directed graph. Okay, and it's acyclic, no cycles. So it's called DAG. Okay. Now, one problem with SSSP is that for general graphs where you have cycles, right? Cycle is a major problem. Why? For example, I give you this particular example here. Okay, 0, 1, 4, 2, 3. You see that there's this cycle here, right? Yes, 0, 1, 2, 4, 0. Yes. So given this cycle, this particular edge, 2, 3, can be actually relaxed multiple times depending on what path you take, right, to reach this particular edge. If I use 0, 1, 2, 3, I'll relax this one once, right? If I use 0, 4, 2, 3, I'll relax it once also, right? So if let's say I'm doing Bellman-Ford, okay, and then the order of edge relaxation is like this: 0, 1, then 0, 4, then 1, 2, then 2, 3, then 4, 2. So after the first iteration, what do I get? Basically, I would have relaxed 0, 1, correct? I get 3, and then I would relax 0, 4, so I get 3 here also, right? Then I relax 1, 2, so 3 plus 2, I should get 5 lah. Yeah, I should get 5, doesn't matter, 5 here, okay, remember? Then I will relax 2, 3, right, which is 5 plus 3, I get 8 here. And then finally, I relax this one, 4, 2. Can I relax 3 plus 1? 4 is better than 5, right? So I get 4 here. But then that's the end of the first iteration, right? And then you find that actually, if I had relaxed 4, 2 first, before I relax 1, 2, right, then this path, this better path, 0, 4, 2, 3, would have been found, right, before I actually use this worst path. But because of the order of relaxation, I actually found this worst path first, right? And then after that, I will end the first iteration. Then I need one more iteration, then I will find the correct shortest path, okay, to 3. Yeah? So the problem here is what? It's because of this cycle, right? Yeah? I can take 2 different paths. And there's actually no good way of determining the order of edges to relax when you have cycles in your graph, okay? Other than actually exploring those cycles themselves, okay, which is a hard problem anyway, okay? So, now, if the graph has no cycles, is a directed acyclic graph, okay, then this issue disappears, okay? So, actually there is a way for me to order all the edge relaxation so that I can just remove for Bellman-Ford, I remove the outer V minus 1 passes. I just replace it with 1 pass. And then go through all the edges, okay, in that order, and that's it. I would have found the shortest path to every other vertex, to every vertex from the source vertex. Okay? So, how do we, okay, what kind of order should we give? What kind of order should we give to the edges? Basically, we just compute them so that we can give a topological ordering to the vertices. And then we go through the vertices from left to right and then relax all the outgoing edges in that order. Okay, just once. That's all you need. Okay, so why does this work? Why do you think that? Just giving everything in topological ordering, and then I go through all the vertices from left to right, and then relax all the outgoing edges, that will work. Just once. Why? Okay, the main idea is this. Okay, for example, I give you the topological ordering of a set of vertices. Okay? In the topological ordering, all the edges will be pointing where? Left to right, correct? You won't have edges pointing like this. Correct? You won't have edges pointing. You will only have edges pointing here, for example, here. Okay, here, like that. Okay, like that. And so on and so forth. Right? They're all pointing to the left. No edge pointing backwards. Okay? So, which means that, for example, if I process all the vertices, right, in this direction, okay, left to right, process means that I go through them, every one of them, I relax all the outgoing edges. Okay? By the time, for example, let's say I hit this particular vertex. All possible vertices that can affect this vertex, okay, in terms of shortest path, would have all their outgoing edges relaxed already, right? Correct? And then everything in front of it, to its right, they cannot affect it, because there's no edge pointing back to it. Okay? Which means that by the time I hit any vertex, I would have already computed the shortest path. Okay, that's the idea. So just in one path like this, from left to right, I would have found the shortest path to every vertex from the source vertex. Okay, so that's the idea. So this algorithm is also known as one-pass Bellman, because you replace the outer V minus 1 loop, right? You've just one pass. Okay, so it's called one-pass Bellman-Ford. Okay, so you will see this one again when we deal with dynamic programming next week. Okay, basically this particular thing, DAX, okay, is a foundation of dynamic programming. Okay, as you will see next week. So we'll revisit this. Okay. Okay, so let's try on Visual Algo. Okay, let's try running our one-pass Bellman-Ford on this particular graph. Okay, as you can see, this graph is a DAG. It's directed, right? All the edges are directed. They are not bidirectional. They are all directed in one single direction. Okay, and there are no cycles. Yeah. Okay, so now, before we start, we must give a topological ordering. Right? So can you remember how we compute topological ordering? We use DFS, right? So we can start from any vertex. Okay, we just do DFS, then we post-process all the vertices in the sense that we post-process them by putting them into a list, right? And then at the end, we just reverse the list. Okay, that will give us a topological ordering. So one possible topological ordering for this will be 0, 2, 1, 3, 4, 5. Okay, you can actually draw this out, then you'll see that all the edges will point to the right. Okay, so let's go through, okay, all these vertices in this order, okay, and perform a relaxation. So let's look at this. So we click this one. It's called dynamic programming. It's actually dynamic programming, so we'll see next week. Okay. So let's start from vertex 0. Okay, that's source vertex. Okay, so vertex 0. So vertex 0, yeah, I start from vertex 0. Vertex 0 is here. So I will try to relax 0, 1, and 0, 2, right? Right. So what do I get? Relax 0, 1, I get 1, right? Relax 0, 7, I get 7. Yeah? 0, 2, then I get 7. Next, I'll relax which one? Vertex 2, right? I go to vertex 2. Then I relax vertex 2. So vertex 2 has only one outgoing edge, so we'll try to relax 2, 4. So 7 plus 4 better than infinity, okay. Update. So it's 11. So I finish vertex 2, then I go to vertex 1. Vertex 1, try to relax 1, 3, and 1, 5, right? So 1, 3 gives you 10, right? So update, 10. Then 1, 5 gives you what? 16, yes, so you get 16. Okay, then after that finish, I will try to relax vertex 3. Right? Vertex 3, we will try to relax 3, 4, and then 3, 5. 3, 4, can it relax? 10 plus 10, no, not better than 11, right? So no change. And then 10 plus 3, is it better than 16? 10 plus 5, is it better than 16? Yes, it's 15, so update. Okay, after I finish 3, I will try 4. So now relax edge 4, 5. 11 plus 3, is it better than 15? Yes, it's 14, so update. And then after I go to 5, 5 has no outgoing edges, finish. So one pass, you see that this is actually the shortest path spanning tree. Okay, the correct shortest path spanning tree from source 0 to every other vertex in your graph. Okay, so it's called one pass Bellman-Ford, or DP, or dynamic programming. Okay, let's go back. Okay, well, anyway, we will look at this again next week. Okay, so this is the third special case. Okay, when you have a DAG, so you do one pass Bellman-Ford. Next, special case 4. There are two sub-cases here. Okay, 4A, when the graph has no negative weight edge, or no negative edges. Okay, so you have only non-negative edge weights, okay, for your graph. So, in this case, well, Bellman-Ford, you can use Bellman-Ford, okay, but Bellman-Ford actually runs quite slowly, right? Big O, VE. Okay, so if let's say I give you a reasonably sized graph, 1,000 vertices, 10,000 edges, okay, and you see that Bellman-Ford is actually quite slow, 1,000 times, not 10,000, 100,000, so that's actually quite slow. Well, in the worst case, E can be what? E can be V squared, correct? So if I have 1,000 vertices, then E squared will be 1 million, then V cubed. V times E will be V cubed, right? That will be 1 billion, so it's actually quite slow. In fact, if I have anything more than 10,000 vertices, then Bellman Fault is really very slow already. Yeah. So, for this case, okay, when I have a graph with no negative edge weights, okay, I don't actually need to use Bellman Fault. Okay, there is a faster algorithm that can solve for this kind of graphs. Okay, this is called Dijkstra's algorithm. Okay, now, of course, there are a lot of practical cases where graphs don't have negative edge weights. Yeah, for example, if a graph representing the distances between cities, you have negative distances, right? Right? Yeah. Or traveling time, without wormholes. This time, imagine no wormholes. It's normally traveling on the road. Okay, so you take positive time, right? So these kind of graphs don't have negative weight edges. Okay, so there's a faster algorithm that actually exploit this kind of graphs with no negative edge weights. So this is Dijkstra's algorithm, which is the main algorithm we will look at, okay, for this lecture. Okay, so there will be two versions of Dijkstra that we'll be looking at. So let's look at the first version, okay, or the original version of Dijkstra's algorithm. Okay. So key idea of this original Dijkstra's algorithm is like this. Okay, formal assumption: the edges are non-negative. Okay, for each of the edge in your E, W of UV is actually bigger or equal to 0, non-negative. Okay. So the key idea of Dijkstra's algorithm is like this. Maintain a set of solved vertices. Okay, so a set called solved, okay, whose final shortest path weight or final shortest path cost has been determined. Okay, in the beginning, solved only contains the solved vertex S. Why? Because that's the only one we know. Right? Take zero cost to reach S from S itself. Okay. Next, I will repeatedly select a vertex U that's not inside solved. Okay, so it's inside V minus solved lah. Okay, your vertex set minus those in solved. Okay, so you select U with the minimum shortest path estimate. Okay, the minimum DU. Then you add U to solve, and then relax all the edges out of U. Okay. So this entails some kind of a priority queue, right? Why? We need an extra data structure. It's not just your D distance array or your predecessor. We need an extra priority queue. Why? Minimum shortest path. Yes, because we want to always keep track of the vertex with the minimum shortest path estimate. Okay? And this is actually dynamic. It's not fixed, right? Because wherever you relax edges, these things will change, correct? So you always want to keep track of that current minimum shortest path estimate. Yeah, so you need a priority queue. Okay, next you'll see this choice of relaxation is actually greedy. Why? Because we simply pick the current smallest one. Okay, and then we say that, okay, I process this, I take this one, I process all its outgoing edges, I relax all its outgoing edges, then I'll put it inside solve, and that's it. Okay, it is solved. For this particular vertex, I have already found the shortest path cost. Okay, so this is greedy. Okay. Yeah. So here's what I mean. If I take it out of the priority queue, I put it in solve, I never enqueue it again. Okay, I never enqueue it again. Okay, but ultimately this algorithm will still give you the optimum result. Okay, it will still give you the optimum result. Okay, but since it is greedy, you have to prove that it's correct. Okay, so later on, hopefully I can explain the proof to you. Okay, so more details on Dijkstra's algorithm. Okay, first I said we need a PQ. Okay, so what does the PQ store? We store an integer pair, okay, which is the shortest path estimate for a particular vertex V. So you store here D, which is the current shortest path estimate, and then V, the vertex. Okay, so D must be equals to the distance array V, right? It must be equal to this. So you don't do away with your distance array, you still have your distance array. Okay, so whenever you relax an edge, you must update the distance array, and then you must also update the pair inside the priority queue. Yeah. Okay. So as initialization, you will enqueue this pair, infinity and V, for all vertices. Okay? except for source. Source you enqueue 0s, because that's the only one we know, right? 0, okay? So at the beginning, you already store all the vertices, okay, inside your priority queue. Okay, so there will be what? V number of items in your priority queue, correct? Okay, next is the main loop. Okay, the main loop will be like this. Keep removing the vertex U with the minimum D from the priority queue. Okay, and then put it inside solve. And relax all its outgoing edges. Okay, this is called processing the vertex. Okay, processing the vertex means I relax all its outgoing edges. Okay? And you keep doing this until the priority queue is empty. When it's empty, everything will be in solve, right? That means that you have found the shortest path to every vertex, okay, in your graph. Okay? Now, when you relax an outgoing edge, that means that when you process the vertex, right? A vertex U, for example, I relax the edge UV. You find that, oh, I can relax it. Then, of course, I will change the distance matrix. Okay, the distance, I will change dV. At the same time, I must go into priority queue, find the entry for V, right? And then change D of V, okay, for that entry. So, you need to update the shortest path estimate in the PQ. What does that entail? You need a decrease key operation, right, for your priority queue, correct? Now, if you have gone through PS1, so do you think you can use the Java priority queue if you need the decrease key operation? No, right? Because Java priority you don't have a decrease key operation. Then you already hit the first problem in using original Dijkstra. I want to use Java priority queue, but then I need a decrease key. I don't have that. So what can you do? Write your own binary heap implementation with the decrease key operation, right? Or what is the other option? What did we say in tutorial? You can actually, anything that binary heap can do, what can do? Balanced BST can do, right? Right? You can actually implement your priority queue using a balanced BST. Okay? Unfortunately for you, Java has its own balanced BST, right? Like 3 maps and 3 sets. Yes, so you can make use of that in order to implement your PQ. Okay, but you just cannot make use of the Java priority queue class. Okay? Okay, so let's try out Dijkstra's algorithm. Okay, here I give you another very simple graph. So this is a directed graph, okay, and the edges are non-negative, okay, all of them are positive, okay, no negative weight edges. Okay, let's try out Dijkstra's original algorithm. Okay, let's try it from source vertex 0. Okay, source vertex 0. So same thing. The shortest path estimate for source vertex 0 will be 0, everything else will be infinity. And then as initialization, like I said, you enqueue one entry in the priority queue for each of the vertices, right? So you enqueue 0, 0, infinity 1, infinity 3, infinity 2, infinity 4. Yeah? Okay. Then you have something like this. So let me just write it out. You have 0, 0, you have infinity 1, infinity 2, infinity 3, infinity 4. Yeah, inside your priority queue. Okay. Now I will start the loop now. The first thing that is dequeued will be which one? 0, 0, right? So the source will be dequeued. It will be taken out. And then it will be put in solve. 0 will be put in solve. And then I will what? Process it, right? I will relax all its outgoing edges. Okay, so I will relax 0, 1, 0, 2, 0, 3. Okay, so what do I get? 0, 1 will be 0 plus 2, so I need to update the weight, right? So, of course, I'll update distance matrix, the distance array. You always update that. But at the same time, you need to go into the priority queue and update the shortest path estimate, right? So this one will change. Oops. So this one will change to 2, right? Yes. So change to 2. After that, I will try to relax 0, 2. Okay, it's the same 0, 2 will change. This one will give you what? Yes, it will give you 6. Okay, then after that, 0, 3. Right. So 0, 3 will change. This one will give you 7. Okay? So you can imagine what is happening inside the priority queue. Okay, so I am not going to change it now, it's a bit troublesome. Okay, but you can imagine what's happening. Yeah. Okay, so let's just look at the graph here. Now, which one will be taken out? Next. So this is the end of the first iteration. So which one? 2, 1, right? Because that's the smallest. Yes. So 2, 1 is taken out. So now I will relax 1, 3 and 1, 4. So 2 plus 3 better than 7. Yes. Update it. Okay. 2 plus 6 is it better than infinity? Yes. Update it. Okay. Then after that 1, 0 and 1 will be solved already in solve. Okay. After that, which one is taken out? 3, 5, right? Yes. 3, 5 taken out. Then I will try to relax the edge 3, 4. So 5 plus 5 is better than 8? No. Yeah. So no relaxation there. But now 3 is done. Okay. After that, I'll take out which one? 2, 6, right? Okay, so 2 is taken out. So 6 plus 1, is it better than 8? Yes, it is. So update. Now 7. And 2 is done. After that, you're left with 7, 4 inside the priority queue. So take that out. No outgoing edges. Done. Okay? So the priority queue is empty now, and you find that everything is in solve with the correct shortest path cost computed already. Okay? And this will be the shortest path spanning tree. Okay? Okay, let me just try from another vertex. Let's try from source vertex 1 instead of 0. Okay, source vertex 1. If I start on source vertex 1, you just eyeball this graph, right? You will find that there are actually certain vertices you cannot reach. From just now, I start from vertex 0, I can reach every vertex. Okay, this is a directed graph. Okay, but if I start from vertex 1, you see that there are actually some vertices you cannot reach. Okay, let's see what happens if I run my Dijkstra's algorithm. Okay, so I start from 0, I start from source 1, then I will relax what? 1, 3, and 1, 4, right? Right. So this one can relax, so 3 will now have shortest path estimate 3, and 4 will have 6. Yeah? Then after that, I will take out 3, 3, correct? Then 3, 3 will try to relax this one, 3, 4, nope. And then after that, I'll take out 6, 4, right? 6, 4, nothing. After that, the only 2 remaining now in the priority queue will be infinity 0 and infinity 2. Right? So at this point, when you see that the one that has DQ has infinity as the shortest path estimate, that means that it is not reachable. It's something that's not reachable, and everything else inside the priority queue must not be reachable already. So at this point, you can actually shortcut your Dijkstra's algorithm and stop it. Okay? I mean, if you continue, you'll find that, well, 0, infinity plus 2 doesn't work, right? It doesn't relax anything, right? Infinity plus 6 also doesn't update 2, right? Infinity plus 7 also doesn't update 3, okay? Then you finish with 0, then 2 also, infinity plus 1 does not update 4. And that's it. Okay, so that's one way to shortcut Dijkstra's algorithm. Once you find that the minimum shortest path estimate that you DQ is infinity, then you can stop already. Okay? Okay, so any questions at this point? No? Quite understandable, this algorithm, yeah? Okay, now, this is obviously a greedy strategy, right? Because you always pick the one with the minimum shortest path estimate and then put it in solve and say that, okay, this is already solved. I have actually found the shortest path to this particular vertex. And all I need to do is just process it, okay, relax all its outgoing edges. Okay? So, why does this greedy strategy work? That means that why is it sufficient only to process each vertex once? Okay, why don't I need to enqueue it multiple times? Take it out, enqueue it again, take it out, enqueue it again. Okay, I need to prove it. Okay, this is greedy strategy, so I need to prove this. Okay, so in order to prove this, let me define a loop invariant. Okay, the loop invariant is basically something that is true at the start of your main loop for Dijkstra's algorithm and also true at the end of the main loop. Okay, so that's called loop invariant. Okay. So the loop invariant is like this. Every vertex V in the set solve must have the correct shortest path distance from the source. Okay, that is, D of V must be equal to delta SV. Okay, delta SV is the actual shortest path cost from S to V. So D of V, the estimate, must be equal to this once V is placed in the solve. Okay, so this is the loop invariant. So initially, is this true? Must be true, because at the beginning I only put source into solve. Okay, so it must be true. Okay, D of S is delta SS, which must be 0. Yeah. Next, Dijkstra's algorithm will iteratively take the next vertex with the lowest DU, right? The lowest shortest path estimate, and put it into solve. Now, is the loop variance still valid at this point onwards? Hard to say. Okay, so we must prove it. We must prove that it's correct. Okay, so in order to prove that this is correct, I need to first prove two lemmas to help me. Okay, the first lemma is this. A subpaths of a shortest path are themselves shortest paths. Okay, so let P be a shortest path. Okay, so P is like this. It contains a sequence of vertices. Okay, V0, V1, V2 until Vk. Okay, let Pij be a subpath of P. So Pij will be some vertex Vi, okay, within P, okay, up to some vertex Vj. Okay, where I is smaller or equal to 0 and smaller, where I is bigger or equal to 0 and smaller or equals to k. Okay, and j is bigger or equals to j, smaller or equals to k. Okay, so it's some subpath. Pij is some subpath of P. Okay, from vertex Vi to vertex Vj. Okay. So, proof by contradiction. Okay. Suppose we have a shortest path like this. Okay, P looks like this. So you have V0 going to some path from V0 to Vi. Okay, so this is path P0i. And then from vertex Vi to vertex Vj, which is the subpath, right, Pij, right? Correct? I have this path, Pij. Okay, and then from Vj to Vk, I have this path, Pjk. Okay. Now assume that Pij is not the shortest path. Right? Pij is a subpath, right? So contradiction means that, well, the subpath of the shortest path is not a shortest path. Right? Proof by contradiction. So assume that Pij is not the shortest path. So if this Pij is not the shortest path, then there must be some shortest path, right? From Vi to Vj. Right? If there is a path, there must be a shortest path. Right? So let's say this shortest path is Pij prime. Okay? Now, if I replace Pij with Pij prime, wouldn't I get an even shorter path for P? I would, right? Then that's a contradiction that P is actually the shortest path. Right? So that's a contradiction. So that establishes the fact that subpaths of shortest path are themselves shortest paths. Yeah? Then this part? I think it's quite understandable, right, this one. Okay. Next, second lemma. Okay. Second lemma is actually a property of our algorithm. Okay, as it works on a non-negative weighted graph. Okay, so this lemma says that after a vertex V is added to solve, D of V will not change thereafter. Okay. Okay, it makes no claim that D of V is actually correct. It's equals to the actual shortest path cost, but it will not change after that. Okay, that's all this lemma is saying. Okay. So again, proof by contradiction. Okay, let's say you have a path P from the source vertex to vertex V. Okay, when V is added to solve. Okay, so the path looks like this. S, there's a path to some U, and then U is the predecessor of V. Okay, along this path from S to V. Okay. So this is the path that I have from source to V at the point when V is added to solve. Okay. Now suppose at some later point you find that there's a better path P prime. Okay, this is proof by contradiction, right? So I have a better path P prime means that D of V changed right after it was actually put in solve, because later I found a better path, so it changed. Okay. So suppose this path is called P prime, and then you have the path looks like this, from source to some u prime, and then u prime has an edge to v. So u prime is now the predecessor of v. It is a different path. Okay, different path. Now, by the algorithm, our Dijkstra's algorithm, u prime must be added to solve later than u or v, right? Must be. If it was added earlier, then what will happen if I add this one into solve? I will try to relax all its outgoing edges, right? Then I would have already relaxed this edge, right? uv, right? Then this better path would have been found earlier than p, right? So there's a contradiction that actually was found later on. So u prime must have been actually added later to solve than either u or v. Okay? Can? Now, then, when v was added to solve, okay, means this, using this particular path, right, when v was added to solve, okay, d of v must be the smallest among all vertices not in solve, right? That's how it works, right? It must be the smallest, yeah? Yeah, correct, okay? So, that means that at the later point when u prime is added into solve, d of u prime must be bigger than d of v. Why? Because, number one, our edge rays are all positive, correct? You can imagine something like this. Okay? V. Okay. This is the set V minus solve. Okay? Then I have another set solve. Right? So at the point when V was added here, d of V must be the smallest among all other vertices here, right? Right? So of course some vertices here inside V minus solve, they haven't even found a path yet, so it's infinity. Some of them have found some path. Based on what? Based on vertices here, right? You relax the edges of vertices here, right? So you found some path, but all of them have a bigger value, have a bigger, shortest path estimate than d of v. So at the point when d was added here, it must be the smallest. Correct? Now, later on, when you add any other vertex into here, can the value go down? Cannot, right? Why? Because they must be based on edges that comes from things here, right? Yes? So it either came from some vertex which was added later than V, or when V relaxed its edges, right? Since these edges, none of them are non-negative, d of any vertex here must be bigger than d of V. Must be bigger than d of V. So since u prime is added later than v, d of u prime when it was added must be bigger than v. Yes? Since it's bigger than v, it must be bigger than d of u also. Right? Because here, u is the predecessor of v, right? U must have been added into solve even earlier than v. Okay? Yeah. So we establish this fact. That means that what? This path, cos s to u, must be smaller than this path cos, right? But I say that p prime is a better path than p. So what happens? How can I get a better path? Only when what? This edge, u prime to v, is negative. That's the only way you can bring down the cos, right? So that it is better than p. So this is a contradiction. Okay, this is the contradiction that my graph only has positive weights or non-negative weights. Okay? Yeah? Okay, so I hope you get this point. Okay, so we have established the fact through this lemma that after you add a vertex into solve, that it will not change after. But I haven't established the fact that it actually correctly computes the actual shortest path cos. The dv, after you have put it in, after you put v into solve, right, is the actual shortest path cos. Okay? So now this is what we are going to prove. Okay? The correctness of our greedy strategy. That means that once it is put into solve, not only it does not change, it must be the correct shortest path cos. Okay, when it is put in solve. Okay. Again, proof by contradiction. Okay, proof by contradiction. Suppose u is the first vertex added to solve, where d of u is not equals to the actual shortest path cos delta su. Okay, suppose U is the first one. This is the first one. Okay, now observation. U cannot be source, S, correct? Source is always correct. Okay, source is always correct. So it must be added at some later point. Okay, some later vertex is added to source. Okay? And if U is reachable from S, there must be a path from S to U, right? And if there's a path, there must be a shortest path. There must be an actual shortest path from S to U. Except that we didn't compute this shortest path correctly. That's what we are doing here. Okay? Now, as a fourth point here. The fourth point here is that every vertex, before I add U, must have their shortest path computed correctly, correct? Because I say U is the first one which was computed wrongly, right? But now there's a question. Yes, they can be computed correctly, but they might be computed correctly after they are added into solve, not at the point they're added to solve, right? But I have lemma 2, right? Lemma 2 says what? Once the vertex added to solve, it's not changed anymore, right? Now, since every vertex before I add U is correct, and once I add to solve, I cannot change it. It must be correct at the point when I add it. Okay? Yeah? So that's what the fourth point says here. Okay? Now, I said, if U is reachable from S, then there must be a shortest path from S to U. Right? So there can be two possible configurations for the shortest path from S to U. And this shortest path was actually not chosen when U is added to solve. That's why it was wrongly computed. Okay? So it looks like this, first configuration. Okay, you have some path from S to some vertex R, okay, in solve, and then from vertex R you will exit solve, okay, to go into V minus solve. Okay, in the first configuration, there's a direct edge from R to U. Okay, in the second configuration, you have an edge from R to T, okay, which is in V minus solve, and then from T you have some path from T to U. So in the first configuration, this is the actual shortest path. In the second configuration, this is the actual shortest path. Okay, but we computed wrongly, so that means that we actually use some other path like that. Okay, some other path like this. Okay, to actually put U into solve. Okay, it's the wrong one. Okay, wrong one. Now, if I look at both configurations, okay, R, this R here, it is the last vertex inside solve, right, before I exit solve, right? Right? So since it is already in solve, and it must have its shortest path correctly computed already, right? So D of V must be equal to delta SD, right? Okay, then if I look at this first configuration, if this was already computed correctly, when I put R into solve, right, what happens? The algorithm will just relax all its outgoing edges, right? So I must already relax this edge, right? If I relax this edge, then the shortest path cost to U must be computed already, right? Because I said this is the actual shortest path cost. Okay, so there's a contradiction that U is computed wrongly, right? Yes? No, it cannot be computed. It must be computed correctly. Okay, so this defeats the first configuration. Okay. Now, second configuration. Same thing. Okay. R here must be computed correctly. Yes? And because R is computed correctly, it must relax all its outgoing edges, right? And then T here must also be computed correctly, right? Why? S to T here, okay, this particular path, S to T here, is a subpath of S to U, right? The shortest path of S to U. Based on our first lemma, what does it say? This subpath must itself be a shortest path. And I would have found it when I relax R. Okay? When I relax this particular edge. Okay? So, that means what? Once I have relaxed this particular edge, the shortest path to T must have been found, right? So, shortest path to T have been found means that T must have been put into solve before I even put U into solve. Correct? Because I use this wrong path, right? This wrong path to put U into solve, right? This wrong path must be bigger than this shortest path, right? And definitely the shortest path from S to T must be smaller than this wrong path, right? Correct? Huh? Correct? Since it's smaller, when I DQ t first, right? Correct? Not u first, right? So u must be inside solve when I actually put u into solve. Okay? So this is also a contradiction. What's the contradiction? The contradiction is that both t and u are in v minus solve when I put u wrongly into solve. Cannot be the case. T must already be in solve. Okay, so you reach a contradiction. Okay. So since in both configurations you reach contradiction, that means that u must be computed correctly, right? U must be computed correctly. And since there's no first vertex that's computed incorrectly, the entire algorithm is correct. Okay? Can? Okay, maybe take a little while after the lecture, try to process. Okay, try to process. Okay, so basically this whole bunch of wordy stuff is what I said. Okay. Okay, so I just proven that original Dijkstra's algorithm works correctly. Okay. For non-negative weighted graph. Now let's analyze the runtime for original Dijkstra's. Okay. Now in original Dijkstra's, each vertex will be only inserted and extracted from your priority queue once. Correct? Yes? Because we insert them all at the beginning, correct? Insert them all at the beginning. After that, we simply update them whenever we get a relaxation, right? Then after that, we only DQ them once. Right? After you DQ them, we'll put them into solve. That's it. They are never re-enqueued into the priority queue again. Okay? So, since they are V vertices, we only insert and extract them from the queue big O of V time. Okay? All of them. Okay? Now, each insert and extract runs in only log V time, right? Because they are only V items, maximum V items in your priority queue. Yeah. So if you use a binary heap for your PQ, then extract min big O of log V time, right? If you use a balanced BST, find min also log V time, right? Right. So altogether for this particular step, we will take big O of V log V time. Yeah. Okay, next. Every time you process a vertex, that means that you take it out of the queue and process it means you relax all its neighbors, right? Okay? So in total, all the E edges are actually processed, right? Because you actually process each vertex once. Okay, so you process each of the edges also once. So in total, all E edges are processed. But you only do it once. Yeah, each edge only once. Okay? So same thing when you relax. Imagine I process it, I actually relax the edge. So imagine each edge causes a relaxation. Then I need to call the decrease key, right? Okay, decrease key function. So you can actually implement decrease key in using a binary implementation, O log V time. Right? If you have done PS1 and then you try to do this, you will find that it's O log V time. Okay, even if you don't do the decrease key or binary heap, well, in the balanced BST, what do? You just delete the old entry, reinsert the new entry. Right? So deletion, insertion, O log V time. Still, okay? So for this one, total time is, I said, you can use a tree set if you are doing balanced BST. Okay, so total time for this particular part will be V times log, E times log V. Okay, so altogether it will be V log V plus E log V. So it's V plus E log V. Okay. So why don't we just say E log V lah? Why do we say V plus E log V? Okay, notice that these graphs, they might not be connected graphs. So V and E are independent variables. You might have more vertices than you have edges actually, okay, in some graphs. Okay, so we'll keep them, in general, we keep V and E as independent variables. Okay. Now, of course, in the worst case, E can be V squared, right? Then this algorithm will be V squared log V. Okay, in the worst case. Okay, at this point, any questions? Any questions at this point? Okay, no question. Then let's try original Dijkstra's on this particular graph. Okay, let's try. Okay, this particular graph, you actually have a negative hash rate. Okay, this one, 2, 3 is minus 10. Okay, let's try original Dijkstra from source vertex 0. Let's see what happens. Okay. So from source vertex 0, then I will relax all outgoing edges. So 0, 1, I'll relax. 0, 2, I'll relax. Yes. Then I will relax which one? Vertex 1, right? Vertex 1, I'll relax. So I will get 3, 3 for vertex 3. Okay, then after that, I'll relax which one? Vertex 3, right? 3 will relax edge 3, 4. So for 4, I will have 6, right? Then after that, what happens? Then I'll take out 4, right? 4 has no outgoing edge. That's it, right? Right? But there's still one more vertex inside my priority queue, right? 2, right? So 2 will now try to relax this edge. 2, 3, right? So this is a negative hash rate, right? So 10 plus minus 10 gives you what? 0, right? So you will do this. So D of 3 will be changed to 0, right? Then after that, you will try to update. Oops. Then you will try to update vertex 3 inside the PQ. But is vertex 3 inside the PQ now? No, I already dequeued it. I put in solve already. Then you can't find it. And then you don't do anything. Then after that, after I take out vertex 2, the queue is empty, right? And that's the end of the algorithm. Okay, so what do you get? You get 0 here. But then now, did I get the correct value to 4? No, right? The correct short answer is actually 0 plus 3, which is 3. Okay? So you'll find you have something like this. Ding, then. That's the end, right? Okay, that's the end. And you find that vertex 4 is not computed correctly. Okay? So, original Dijkstra does not work on graphs with negative weight edges. Why? Because with negative weight edges, a vertex might need to be processed multiple times, right? Not just once. Yeah, not just once. Okay. And with original Dijkstra, we don't process it. We just take it out, put in solve, and that's it. Okay. Okay. So we don't get the correct answer there, and the issue is with vertex 3. Okay. Okay, so how can we modify Dijkstra in order to overcome this weakness? Okay, we can do that. Okay, so we have a second implementation for Dijkstra's algorithm. It's called modified Dijkstra's algorithm. Okay, that will work with graphs that have no negative weight cycles. So this is the other case for special case for the other subcase. So it's 4b. Okay, so if the graph has no negative weight cycles but can have negative weight edges, okay, then we will use this modified Dijkstra algorithm. Okay. So for practical cases, okay, SSSP problems are basically performed on graphs where the edges may have negative weights, but then no negative cycles. So of course there are lots of cases where you only have positive weights, but there are also some cases where you have negative weights but no negative cycles. Okay, example is what? You travel between two cities, okay, using an electric car. Okay, so if you are traveling on flat ground, you use the battery power. Right? You go uphill, you use the battery power. But then when you go downhill, you need to use the battery power. No need to use gravity. Right? So when you're going downhill, you can actually recharge the battery, yeah, due to your kinetic movement of the car. Okay, so then if you want to represent a graph, right, of the energy usage, okay, or the charging energy, I mean the usage or the charging of your battery, right? So you can link, for example, flat ground, I use energy, right? So if we use energy, then we plus is positive edge. Or from flat ground to high ground, plus. But when we are going down from a high ground to flat ground, negative, because we are recharging the battery. Okay, so it's a negative edge. Okay, we can have negative edge. But in this case, can we have a negative cycle? Imagine that I have a series of hills that I put in a circle. Okay, can I have a car that goes up the hill, down the hill, up the hill, down the hill, up the hill, in a circle, then keep going like this, right? And then I keep charging. Whenever I go down here, I charge, then I go up here, I use up the amount of energy that I charge out, then go down here, up here. I can keep cycling like this forever, right? Is that going to happen? No, because number one, energy conversion is not perfect, right? Most of the kinetic energy is actually lost through friction. Yeah, it's not perfectly converted into the power inside your battery. Okay, and if you can build a machine like this, you can keep on cycling forever without any additional power source. Right? What do you get? You get what you call a perpetual motion machine. Have you heard of that before? It's a holy grail for a lot of people in the past, before scientists actually proved that there's no such thing as a perpetual motion machine. So in a closed system, you want energy input in that system, right? You use up all the energy. It's entropy. Okay, so I mean, people are still trying to come up with a perpetual motion machine nowadays. People say it's impossible. Physicists will say it's impossible. Okay. Yeah, so you cannot have a negative cycle. In fact, you cannot even have a zero cycle, zero cost cycle. Okay, not to say a negative cost cycle. Yeah. Okay, so like I said, with negative ash rates but no negative cycles, okay, we have a modified version of Dijkstra to handle this case. Okay, so for the modified implementation, the formal assumption is like this. The graph has no negative weight cycles, yes, but it can have negative weight edges. Okay, key ideas for this modified implementation is like this. You allow a vertex to actually be processed multiple times, okay, multiple times, instead of only once. That means that we might enqueue, dequeue it multiple times, okay. Now, for this particular modification, okay, we only need to make use of the Java priority queue. Okay, this time we can make use of the Java priority queue, okay, in order to enqueue, find out which is the next vertex you need to process, okay. What information do we need to store inside the priority queue? Okay, same thing, we need to enqueue the integer pair, okay, for each vertex, which is the current shortest path estimate D for the vertex U, okay, where D is equals to D of U, okay, current shortest path estimate. Okay, here's where, at this point it's still almost the same as original Dijkstra. Okay, but there's one modification we will make where it will be different from original Dijkstra. Okay, we make use of what we call lazy data structure strategy. Okay, what is the lazy data structure strategy? Okay, the main idea is this. You don't have to maintain just one integer pair inside your priority queue. In original Dijkstra, there's only one integer pair, right, for each vertex. Whenever I relax, I need to find the vertex that's being relaxed and then update it, right, the decrease key operation. But in the modified version, I don't need to do this. Okay, what do I mean? What I mean is this. Whenever I relax an edge UV, I don't go into the priority queue, right, and then try to find V, and I update it. What do? I simply enqueue a new copy with the most up-to-date shortest path estimate. That's it. Okay, so that's called lazy because I don't care about the old versions inside the priority queue anymore. Okay, so that's called lazy. Yes. I think you have heard, I think some of you actually use this strategy in PS1, lazy delete. Yeah, this lazy data structure strategy. Okay, so because of this particular modification, we can have actually multiple shortest path estimates inside our priority queue related to a single vertex. Okay, related to a single vertex. Okay, now there's not just one copy but multiple copies, right? Then we have to be careful when we dequeue an entry from the priority queue, correct? Okay. So what do we do when we dequeue? Okay, or extract a pair from the front of the priority queue. Okay, you extract a pair DU. Okay, we need to have one particular condition. Add one condition. We need to check this. Check if D is equals to DU. Okay, the distance array always keeps the most current, most up to date. All I need to check is that, is this the most up to date copy or not? So check D is it equals to DU or not? If it is equals to DU, okay, then I will process it. I will relax all the outgoing edges. If not, that means that it's an outdated copy, I don't care. Throw it away. Okay? Yeah. So how do we get multi-source? I say wherever we relax, if we can relax, we just enqueue a new copy, okay, with the most up-to-date shortest path estimate. Okay. So this is the lazy part. And there's also one advantage of doing this. I don't need the decrease key operation anymore. Right? Since I don't need the decrease key operation, then I don't need the BST implementation. I don't need your own binary heap, custom binary heap implementation of PQ. Just use your Java PQ class. Yeah. Okay, so the algorithm for modified Dijkstra will look like this. Okay. At the beginning, I do init SSSP, okay, is what we always have. Okay, then I will enqueue just one copy first. I don't enqueue everything at the beginning, unlike original Dijkstra. Here, I only enqueue the source, okay, at the beginning. Then same thing, I have the loop, okay, which will loop while the PQ is not empty. I just dequeue from the front of the queue, okay, and then I check whether this D is the most up to date. If it is the most up to date, then I will just relax all the outgoing edges. Okay, so if it can be relaxed, then I update DLB and I enqueue a new copy. Yeah, I just enqueue a new copy instead of trying to find D inside the queue and then update it. Okay. So this is a very simple modification to your code. Okay, let's see whether it works. Of course it works. Okay. Let's try it out. Okay, same graph again, this one, the directed graph. Okay, now let's try the modified version from source vertex 0. Okay, modified. So at the beginning, now it's slightly different. I only enqueue 0, 0. Yeah, then I'll relax everything, all the neighbors of 0. So I relax 0, 1. So I have what? I will have 1, 2. Oh no, 2, 1. Sorry. 8, 2, 1. Then after that, I will have 6, 2. Right. And then I will have 7, 3. 7, 3, and this one is out. Okay. Then after that, which one? 1, right? Right. So this one is taken out. Of course, when you take out, you compare, correct? Is this 2 equals to the current shortest path estimate? Yes, this one is 2, 2, correct? Yes. So I will relax it. I'll process it. So I will relax edge 1, 3, right? So I can relax. So the shortest path estimate go from 7 down to 5, right? So now I don't go here, look for this 3, look for this particular one, and then change 7 to 5. I simply enqueue a new copy. Okay, so I'll have 5, 3. Okay, 5, 3. Okay, now that which one is taken up? Oh wait, I need to relax this one. 1, 4, which gives me 8. Okay, so I'll enqueue this one. 8, 4 also. Okay, then I'm done with this iteration. Then the next iteration, which one is taken up? Sorry? 5, 3, right? So 5, 3 is taken out. So it is the latest copy. Okay. 5, 3, then we will try to relax 3, 4, right? Cannot relax because 5, 5 is 5 plus 5 is not better than 8. Then after that, which one is taken out? 2, right? This one, 6, 2. Yes. Then 6 plus 1, is it better than 8? Yes, it's better. So I update the one for 4. Okay, so I enqueue a new copy here. Let's space it. So it's 7, 4. Okay, enqueue a new copy. Okay, after that, which one is taken out? Either 7, 3 or 7, 4, right? So if you have the same shortest path estimate, then you will compare the vertex number. That's it. So it will take 7, 3 out. 7, 3, no. 7, 3 is actually not the most up-to-date copy, right? Correct? Because now 3, D of 3 will be 5, right? Instead of 7. So I just discard it. I don't do anything with this. I'll take the copy. Okay, next I'll take out 7, 4. 7, 4, yes, is the most up-to-date, but there's no outgoing edges. So that's it. And then I'll take 8, 4. 8, 4 is the outdated copy. And that's it. Your priority queue is empty. Okay? And do I get the correct shortest path. After that, yeah, I do, yeah. So it still computes this correctly, okay? For a positive weighted graph, okay, it's a positive weighted graph. Okay, let's try it for the negative weighted graph. Okay, this one. Okay, now let's try from 0, do the modified one. Okay. So 0, it will relax 0, 1, 0, 2, yes? So 0, 1, 0, 2, relax. And then after that, it will relax 1, 3, right? Right. 1, 3, relax. After that, it will relax 3, 4, right? Then 3, 4, relax. Then after that, it will relax 2, 3, right? 2, 3, yes, no. 4 first. 4 got nothing. Then 2, 3, right? 2, 3, relax. What happens? I re-enqueue a new copy, right? For 3, right? So now I have 0, 3 inside the priority queue. So it's not empty. Then after that, I'll take out 0, 3. 0, 3, relax, 3, 4. Relax. Okay, then after that, take out 4. Nothing, that's it. Priority queue is empty. But you see, because I re-enqueue vertex 3 multiple times, I actually found the actual shortest path to 3 and then was able to relax 3, 4 correctly. Okay, so I actually found the correct shortest path. Okay, using modified Dijkstra. Okay, this one done, correct. Okay, now analysis on modified Dijkstra. What's the runtime for modified Dijkstra? Okay, first we analyze this on graphs with no negative weight edges. Okay. Okay, remember we always prevent the processing of outdated copies, right? By having this condition, right? You always check whether D is bigger than DU. Okay, if it's bigger, then I don't process it. Yeah. Okay. So now, if there are no negative edge weights, okay, then when U, a particular vertex, is greedily processed from the priority queue, that means that I take U, I dequeue U, I find that, oh, this is the most up-to-date copy, right? Then I'll greedily relax all is outgoing, I will place U into source, into solve, right? Right? Then from that point onwards, there can never be another path that will decrease DU if there are no negative edges. Why? That's what we prove, right? With original Dijkstra, right? So it doesn't change for modified Dijkstra. Okay, this part doesn't change. Okay? So that means that each vertex is still processed only once from the priority queue. Okay? That means that I might enqueue multiple copies of it, but I only dequeue and process one of them. One of them. Okay? After I process that one, all the inferior copies, right? After that, I might dequeue them, but I don't process them anymore. Yeah, the inferior copies. Yeah. So each vertex is still processed from the priority queue once. Okay, each vertex. So we'll do this OV time. Yeah. And extract min, in order to dequeue them, is still O log V. Okay, you use the priority queue. Okay. So in total, this part is still big O of log V time. Okay, now you might say, hey, now the priority queue, right, it does not just contain V items, right? Unlike original, because I can multiple copies, so how are you to guarantee that extract min is still big O log V? Okay, you'll see the next slide, it is still big O log V. Okay. Every time a vertex is processed, what do? You simply relax all its outgoing edges, right? Right? So that means that same as original Dijkstra, all big O of V edges are actually processed. Okay, I actually relax. Okay? And we only relax them once, correct? Because from the first slide, we already said we only process them greedily from the priority queue once. Okay? Now, when we relax an edge, of course, if the relaxation is successful, I will enqueue a new copy, right? Yes? SUV, if I can successfully relax it, I will enqueue a new copy of V, right? Inside my priority queue. Okay? So, the question is, then how many maximum, what is the number of copies inside my priority queue? It must be big O of E, right? Right? Because imagine every edge causes a relaxation. Right? So that's big O of E. Okay? And then, E is at most what? E is at most what? V squared, right? V squared, right? You can imagine that a vertex has at most every other vertex have one incoming edge to it, right? So you imagine each of these edges cause a relaxation. So for every vertex, I can have at most big O of V copies. Yeah. So in total, number of items in my PQ is big O of V squared. Big O of V squared, what is the time for extract? Log V squared, right? Log V squared is just what? 2 log V. So it's still log V. Okay, it doesn't change. Okay? Yep. So insert or extract, okay, it will still be log V. Okay, so this part is basically just E log V. Okay, then the first part, the previous slide is V log V. So altogether, V plus E log V. Okay, so the runtime is no different from that for original Dijkstra. Okay, if you have no negative hash rates, what happens if you have negative hash rates? Oh, now that's a different story. Okay, but let me show you this very interesting example. Okay, this is known as Dijkstra killer. Why do you call it Dijkstra killer? Oh, you'll see. Okay, so it's a very interesting formation. It looks like a sawtooth blade. Yeah, it's a saw, right? With the jagged teeth. Okay. So let me try Dijkstra on this, modified Dijkstra on this particular one. Okay, wait, I start from here. Okay, before that, okay, if you look at this graph, there are no negative cycles. Yes, there are no negative cycles, but there are negative edges, right? So you can see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are all negative edges, but there are no negative cycles. Okay, so I can run modified Dijkstra on this one. Okay, let's run. Okay, I start from source 0. Then I will relax 0, 1, 0, 2, right? Okay, we should get source path estimate 16 and 0 respectively. Okay, then after that, I will take 0, 2 out, right? So take vertex 2 out, and then relax 2, 3, and 2, 4, right? We should get 8 and 0 respectively. Then I take 4 out again, right? Then relax 4, 5, 4, 6. So I get 4 and 0 respectively, then I take out 6, right? Then I'll relax 7 and 8, we should have 2 and 0 respectively, then I take out 8, right? We should relax 9 and 10. Okay, now concentrate. Put your attention on this one, on 10. Okay, put your attention here, this one. Okay, at this point, I actually found one path from 0 to 10, right? Which is one 0, 0, I mean 0, 0, 2, 4, 6, 8, 10, right? Which has cost 0. Okay? And after that, I'll take out 10, right? No outgoing edges, that's it. After that, which one I take out? 9, right? 9 has the current smallest cost. Shortest path estimate, like 1. So I take out 9. Now I'll try to relax 9, 10, correct? Can I relax? Yeah. 1 plus minus 2 gives me what? Minus 1. Right? So now I found another path, right? Which is 0, 2, 4, 6, 8, 9, 10. Okay, then after that, I will take out 10, right? 10, no outgoing edge. Okay, nothing. Then after that, I take out which one? 7, right? Vertex 7, right? So vertex 7, try to relax 7, 8. Can it relax? Yes. 2 plus minus 4 gives me minus 2 is better than 0. Okay. So, now 8 is enqueued again, right? Now after that, which one is the next smallest one? 8, right? I take out 8. What happens? The same thing happens, right, as previously, right? You will try to relax 8, 9, and 8, 10, right? Right? 8, 9, 8, 10, and after that, I found another path, right? 0, 2, 4, 6, 7, 8, 10, right? Okay, then after that, which one is the next one? 9 minus 9, right? Which is minus 1, right? And minus 1 will, 9 will now relax 10, right? Then I get yet another path, right? 0, 2, 4, 6, 7, 8, 9, 10, right? Okay, then you'll see that, I'm just going to run it very quickly. You see a cascade. Okay, now I'm just going to run it. That's the end. Okay, you see a cascade. Okay, so if you look at this, if you look at this, let me just rewind it a bit. Then you can see it more clearly. Even rewinding it takes a bit of time. Okay. Now the first path that I used to reach from 0 to 10 gives me a total path cost of 0, right? Shortest path estimate is 0. Then the next better path I find is -1, right? Then the next better path I find is what? -2. Then -3, -4. Do you see? -9, 8, 13, 14, 15, 16, 17, 18, 19, 20, 20 something, all the way to -31, then stop. How do you get this one? You can imagine it's like this. You see that at each point here, 0, 2, 4, 6, 8, there are two possible ways, right? I can take this or this. Okay? There are two possible paths I can take. Either the one going up or the one going to the right. Yeah, this one is the same. Okay, this one is the same. This one is the same. This one is the same. And you'll find that each possibility or each combination is actually tested before you find the final combination, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is the best shortest path. So how many combinations are there here? It's like a binary tree. 0 has 2 possible ones, 2 has 2 possible ones, so it's 2 power 5. Which gives you what? 32 possible paths. Yes? Which is why you get -31. Because the first path is 0, then you keep counting down. So you get -31. So, with this very, this you have to come up with after a lot of thinking. Okay, but it is possible, right? I've shown you one case where actually the time required by modified Dijkstra is what? It's exponential. It's exponential in the number of vertices. Right. Because here what? 1, 2, 3, 4, 5 is actually about half of the total number of vertices already. Right? So it's 2 to the power of big O of n, or big O of v. Okay, it's exponential time. It runs exponential time because it needs to explore so many paths. Okay, in order to find the best path. Okay, anyway, your lab tutor will go through this again. Okay, so you understand this quite well. Okay, so this is not an all-conquering algorithm. Okay, if you have negative, sometimes if you have negative hash rates, you might run in the exponential time. Okay, it can solve it, but it takes a very long time. Okay, it takes a very long time. Okay, but these kind of extreme cases are quite few. Okay, in practice, okay, Dijkstra's algorithm, this particular modified Dijkstra's implementation is much faster than Bellman-Ford. It's even faster than the original Dijkstra. Okay, because you don't need the decrease key operation. Okay. So, now the rule of thumb is something like this. If you know that your graph has very few or no negative hash rates, okay, so you probably want to use modified Dijkstra. Okay, but if you know that your graph has a high probability or it has got negative weight cycles, right? Okay, then use the tighter Bellman-Ford algorithm. Okay. Why for negative, if it has a negative weight cycle, use Bellman-Ford? Okay, this one I haven't showed you. Okay, this one is the last graph I'm going to show you. Okay, this one is a graph with negative cycles. Okay, let's see what modify an original Dijkstra will do. Okay, let's try original Dijkstra from source vertex 0. Okay, so this is a negative cycle. Okay, this is a very simplistic one now. Okay, this one is actually the one that I talked about last week. But let's use this. So there's a negative cycle, very trivial cycle here, 1 to 2, 1 to 2. Yeah. Negative cycle. So, with original Dijkstra, what happens? I start from source vertex 0. Right. Then I will relax 0, 1, 0, 4. Right. Then after that, I'll take out 4, right? Nothing, no outgoing hash, nothing. Then I'll take out 1. Then I'll relax 1, 2. Right? I get 1, 1, 4. Now after that, I'll take out 2, right? Then I try to relax 2, 1. Can I relax? Yes, I can, because 1, 1, 4 minus 42 is better than 99, right? Okay, then you will relax it, you get 71. But, as we have said, for original Dijkstra, once one vertex 1 has been taken out of the priority queue, is no longer inside. right? So even though D of 1 is updated, but you cannot find it inside the priority queue anymore. So you do nothing. And then after that, you will relax 2, 3. Right? And this one gives you 1, 2, 4. Then vertex 2 is done. Then I'll take out vertex 3. No outgoing edge. And then it's done. Okay? So you'll find that, is this the correct path? Is it the correct shortest path? No, right? Yes? Number 1. This one, the path that it took to reach 1 is what? 0, 1, 2, 1. It took a cycle. Right? It actually took a cycle. Okay, so the shortest path estimate here is wrong. Okay, is the shortest path estimate for 2 correct? Also not very correct, because if you have a negative cycle, I can keep going around the cycle. Right? So, like I said, with negative cycle is ill-defined. The problem is ill-defined. Okay, and original Dijkstra gives you the wrong shortest path cost, and it can't tell you whether this graph has a negative cycle or not, because it cannot differentiate this case where the graph has a negative cycle from the case where it only has a negative edge. Okay, the algorithm cannot differentiate that, so it can't tell you. Okay. Now let's try modified. Okay, start from 0. So let's see what modified Dijkstra do. Okay. So 0, it will relax 0, 1, 0, 4, so we NQ 99, 1 and minus 99, 4. And then take out minus 99, 4, nothing. And then take out 99, 1, relax H 1, 2, so I'll NQ 1, 1, 4, 2. Okay, then I'll take out 1, 1, 4, 2, relax 2, 1, right? Then NQ 72, 1. And then I'll NQ 1, 2, 4, 3. Then I'll take out 1, right? Which is 72, 72 plus 15. Yes, it's better than 114. So I'll NQ 2 again with 87, right? Then after that, 87 will, okay, vertex 2 will try to relax 1. It can relax. So NQ 1 again, NQ 3, correct? Then you'll see that 1 and 2 keep being NQ, DQ, NQ, DQ. Vertex 3 is never DQ, but you keep NQing new copies inside. Okay? Then 1 and 2 just keep going, right? Infinitely, or until you run out of computing time or you run out of memory space. Okay? So, it will not stop for modified Dijkstra if you have a negative cycle. Okay? So, which is why, if you know that your graph has got negative cycles, please don't use modified Dijkstra. You cannot tell. Or, well, you can tell, because if you keep a loop that will run an exponential number of iterations based on the number of input vertices. Once it exceeds a certain number, you are sure that, oh, cannot already, there must be something wrong. But then you already run exponential time already, right? So you don't want to do that anyway, right? So if you know that you have a negative cycle, please use Bellman-Ford. It will tell you, okay? It will tell you, okay? Or it's a high probability that you have a negative cycle. And Bellman-Ford will tell you whether you do have it or not. Okay, so we have shown this one. Okay, so we're almost at the end. So Java implementation, no Java implementation for Dijkstras. Okay, why? Because you are supposed to write this yourself, okay, for PS5, subtasks B and C. Okay, actually B and C, yes. Okay, so I have shown the performance of Dijkstra's algorithm on a small graph with no negative weight cycle, so it's okay, they work correctly. Okay, both original and modified Dijkstra. Small graphs with some negative edges, no negative cycles, modified Dijkstra will work correctly. Okay, but original Dijkstra will be wrong. Yes, but for some graphs, for certain graphs, modified Dijkstra might run the exponential time. Okay, might. Okay, but in practice, it's hard to hit this kind of cases lah. Okay, it's hard to hit this kind of cases unless it's purposely constructed. Okay, like what we did, the sawtooth. Okay, now with small graphs with negative weight cycles, then one SSSP problem is ill-defined. Okay, so modified Dijkstra will be trapped in infinite loop, whereas original Dijkstra will stop, but then it will just give you the wrong result lah, and it can't tell you whether there is a cycle or not. Okay, because it cannot differentiate between this case and the case where there's only negative edge weights. and no negative cycles. Okay, so summary of your various SSFP algorithms. General case of a weighted graph, then use Bellman-Ford. Okay, if you have no idea about what kind of input it is, okay, all you know is a weighted graph, then use Bellman-Ford. But if you know it's a tree, use DFS or DFS. If you know it's an unweighted graph or constant weighted graph, use DFS. If you know it's a deck, then use one-pass Bellman-Ford. Okay, topple sort the deck, and then process all the vertices in order from left to right. Okay. Then special case for A and B. Okay, first one, A, graph with no negative weights. Then you can use original or even modified extra. Okay, they will run in big O of V plus E log V time. Okay, which will be better than just using Bellman-Ford. Okay, or case for B where there's negative edge but no negative cycle, you can use modified extra, which will usually run in this time, but sometimes you might run in the exponential time. Okay. Okay, so with this particular lecture, after this, PS5 should now be doable. Okay, so I said it's been released noon today, so you can go and check it. Okay, do it. So sometimes A is quite easy, use what you learned today, plus something you have already done in your previous PS. Okay, sometimes B is also quite okay, what you have learned today and something you have done in previous PS. Okay, sometimes C is the hard one. Okay, sometimes C is the hard one. Okay, you think about it. Okay, so that's it for this lecture today.